Somewhere out at the edge of what the James Webb Space Telescope can see, there is a galaxy that shouldn't be able to exist the way it does. It's massive. It's ancient in the sense that the light reaching us from it left home when the universe itself was barely out of its infancy. And it is doing something that, according to every model astronomers currently have for how galaxies grow up, it simply should not be capable of doing yet. It isn't spinning, not slowly, not irregularly. It shows essentially no rotation at all, a trait scientists have only ever associated with old, settled, fully mature galaxies sitting much closer to us in both space and time. Finding that same behavior in a galaxy from the universe's earliest chapter has left the researchers who discovered it with a genuine, published, peer-reviewed mystery on their hands, and it's forcing a hard second look at some basic assumptions about how galaxies like our own Milky Way actually come into being. This is a real discovery, published just this year in the journal Nature Astronomy, and it's exactly the kind of finding that reminds you just how much James Webb is still quietly rewriting about the universe, one strange, unexpected result at a time. Every detail in this video comes directly from that peer-reviewed research and the scientists who actually conducted it. Not speculation, not exaggeration, just the genuinely strange reality of what this telescope keeps finding at the very edge of what we can observe. Let's start with what astronomers actually expect to see when they look at a galaxy from this early in cosmic history, because that's what makes this particular discovery so genuinely disorienting. When the universe was young, galaxies were still very much in the process of assembling themselves, pulling in gas, forming stars, colliding and merging with their neighbors in a chaotic, ongoing process of construction. Based on decades of observation and modeling, astronomers have generally expected that young galaxies from this era should still be spinning from the momentum of their own formation, gradually settling into more organized, orderly rotation only much later, over billions of years, as they mature and stabilize. A galaxy with no rotation at all is something researchers associate almost exclusively with much older, fully evolved systems, ones that have had enough time for their stars to settle into what's called random, dispersion-dominated motion, rather than the smooth, coordinated spin you'd expect from a young, still-forming system. That's exactly what makes this particular galaxy, cataloged as XMM-Vid1 2075, so difficult to explain. Using the James Webb Space Telescope, an international research team led by Ben Forrest, a research scientist in the Department of Physics and Astronomy at the University of California, Davis examined this galaxy alongside two other galaxies from the same early cosmic era, all formed less than 2 billion years after the Big Bang itself. Among the three, the differences were striking. One of the galaxies showed clear, organized rotation, spinning in an orderly way, roughly consistent with what researchers expected to find. A second showed a more irregular, chaotic structure, neither clearly spinning nor clearly settled. But the third, XMM-Vid1 2075, showed essentially no rotation whatsoever, instead displaying strong, random motion among its stars. The exact signature scientists normally associate with some of the most massive, fully mature galaxies found in the local, present-day universe, not galaxies from the earliest chapters of cosmic history. Forrest himself described the finding plainly, noting that this kind of detailed motion analysis has been done extensively on nearby galaxies, simply because they're close enough and large enough in the sky to study this way from ground-based telescopes. But high-redshift galaxies, the term astronomers use for extremely distant, extremely early galaxies whose light has been stretched by the universe's ongoing expansion, are far smaller and fainter in our sky, making this kind of precise motion study extraordinarily difficult without an instrument as sensitive as Webb. He noted that finding a galaxy displaying such mature, settled behavior consistent with some of the most massive galaxies in the local universe was, in his own words, a bit surprising to encounter this early in cosmic history. To understand exactly why this result challenges existing theory so directly, it helps to walk through what astronomers call a slow rotator, the specific category this galaxy has now been placed into. In a typical spinning galaxy, like our own Milky Way, stars orbit the galactic center in a coordinated, roughly circular pattern, all generally moving in the same direction, producing that smooth disc-like rotation you often see in images of spiral galaxies. Our own solar system, for instance, orbits the center of the Milky Way as part of that same coordinated, roughly 200 million year rotation, one small, orderly piece of a much larger spinning structure. A slow rotator behaves completely differently. Rather than following coordinated orbits, its stars move in more random, chaotic directions relative to one another, a pattern that typically develops over long stretches of cosmic time, often as the result of major galactic mergers, violent collisions between galaxies, that scramble stellar orbits and gradually erase any organized rotational motion the system once had. Picture the difference between a crowd of ice skaters gliding together in a smooth, coordinated circle versus that same crowd, after a chaotic collision, has sent everyone spinning off in random, unpredictable directions. That's roughly the visual difference between a spinning galaxy and a slow rotator. And it's a transformation that normally requires an enormous amount of cosmic time and violent gravitational interaction to actually happen. Finding this exact pattern in a galaxy that existed when the universe was less than 2 billion years old means that whatever process usually takes many billions of years to unfold, gradually transforming an organized, spinning young galaxy into a settled, non-rotating, mature one, appears to have already happened here, at a point in cosmic history when there simply shouldn't have been enough time for it to occur. Researchers are now actively trying to understand exactly how a galaxy like this could have become what scientists call a slow rotator so quickly, and there are a few competing possibilities currently being explored, none of them yet confirmed. One leading idea involves extremely rapid, violent galaxy mergers happening far earlier and far more frequently in the early universe than current models predict, essentially compressing billions of years of typical galactic evolution into a much shorter window of cosmic time. If galaxies in this era were colliding and merging at a dramatically faster rate than existing simulations account for, that alone could explain how a system this young ended up with the scrambled, randomized stellar motion normally associated with much older galaxies. Another possibility involves the galaxy's central supermassive black hole, if it has one, playing an outsized role in disrupting orderly stellar motion much earlier than expected. Through the kind of energetic feedback processes, powerful outflows of gas and radiation that can churn up and scramble the orbits of surrounding stars far more aggressively and far more quickly than gravity alone typically would. A third possibility, and perhaps the most unsettling for cosmologists, is that our fundamental models of how quickly structure can form and settle in the early universe may simply be missing something important, some mechanism or timeline that current simulations haven't properly accounted for. A gap that wouldn't be unique to this one galaxy, but might instead point toward a broader systematic underestimate of how quickly the universe's earliest structures were capable of maturing. This discovery doesn't exist in isolation either. It's part of a much larger, ongoing pattern that has been building steadily since James Webb Space Telescope first began operating in 2022, one that astronomers have started referring to, somewhat informally, as the impossible galaxies problem. Within the telescope's very first year of operation, astronomers began identifying galaxies that had formed within just 300 to 500 million years after the Big Bang, and found that many of these early galaxies appeared far larger, far more structured, and far more evolved than existing cosmological models predicted should be possible in such a short window of time. These early galaxies looked, in the words of several researchers who studied them, almost as if they had skipped their own childhood entirely, arriving already mature and fully formed. The same broader pattern has kept surfacing in entirely different corners of Webb's ongoing observations too. Earlier this year, a separate research team from Texas A&M University, examining a different patch of the deep sky, identified something they nicknamed the JWST quintet, an active, ongoing collision involving at least 5 separate galaxies, captured happening only about 800 million years after the Big Bang. Before Webb, astronomers generally expected that complex mergers involving this many galaxies at once, along with the widespread redistribution of heavy elements produced by dying stars, wouldn't become common until well over 1 billion years after the Big Bang. Finding this kind of complex, chaotic multi-galaxy interaction happening so much earlier than expected, in a compact region of space surrounded by an unusual halo of oxygen-rich gas, adds yet another data point to the same growing puzzle that the early universe appears to have been organizing itself, colliding, and maturing at a pace current models simply didn't anticipate. Dr. Waidahu, the study's lead author, noted that a merger involving this many galaxies simply wasn't expected this early in cosmic history, when interactions were generally assumed to be simpler, usually involving only 2 or 3 galaxies at a time rather than 5. This newly discovered non-rotating galaxy fits directly into that same broader pattern. Another example of the early universe behaving in ways that seem to have moved faster and grown up more quickly than the standard models of galaxy formation currently allow for. It's worth being clear about exactly what this does and doesn't mean, because a discovery like this tends to get exaggerated in translation. This isn't evidence that the Big Bang didn't happen, and it isn't evidence that our basic understanding of cosmic history is fundamentally broken. What it actually represents is something more precise, and in its own way, more interesting. The core framework astronomers use to understand the universe's large-scale structure and evolution, generally referred to as the standard cosmological model, continues to hold up extremely well against an enormous range of observational evidence. What findings like this one are doing is exposing specific, testable gaps in our understanding of exactly how quickly individual galaxies can grow, merge, and mature within that broader framework, details that earlier telescopes simply weren't sensitive enough to observe directly. Every one of these discoveries becomes a genuine, falsifiable data point that theorists now have to account for, refining the details of galaxy formation models rather than overturning the broader picture of the universe's history. That refining process is exactly why a telescope like James Webb matters so much for this specific kind of science. Earlier space telescopes, including the enormously influential Hubble Space Telescope, simply weren't built with the right instruments to properly study galaxies this distant and this faint in the kind of detail required to measure something as subtle as internal stellar motion. James Webb observes primarily in infrared light, which turns out to be exactly the right tool for this job, because as light from extremely distant galaxies travels toward us across billions of years, the ongoing expansion of the universe stretches that light toward longer, redder wavelengths, a phenomenon astronomers call redshift. The farther away, and therefore the further back in time a galaxy actually is, the more dramatically its light gets stretched by the time it finally reaches us. By the time light from a galaxy like XMM Vide 1275 reaches us, much of what was originally visible light when it left that galaxy has been stretched all the way into the infrared portion of the spectrum, which is precisely where James Webb's instruments are specifically designed to observe with extraordinary sensitivity and precision. Earlier telescopes, built primarily to observe visible light, were essentially blind to a huge amount of the fine detail Webb can now pull out of these ancient, distant systems, which is exactly why so many of these early universe surprises simply weren't available to astronomers before Webb launched in December of 2021 and began full science operations the following year. There's also something worth appreciating about just how difficult this specific kind of measurement actually is, even with Webb's capabilities. Determining whether a distant galaxy is rotating, and how quickly, requires astronomers to measure incredibly subtle shifts in the wavelength of light coming from different parts of the same galaxy, essentially detecting whether one side of the galaxy is moving slightly toward us, while the other side moves slightly away. The same basic principle behind how a passing ambulance siren changes pitch as it approaches and then recedes. For a galaxy that appears as nothing more than a tiny, faint smudge of light in the sky, separated from us by more than 10 billion years of cosmic history, extracting that level of internal detail represents an extraordinary technical achievement, one that simply wasn't possible before an instrument with Webb's specific combination of sensitivity, resolution, and infrared capability existed. So here's what I actually want you to take away from all of this. There is a galaxy out there right now, one that existed when the universe itself was barely getting started, behaving exactly like some of the oldest, most settled galactic systems we know of in our own cosmic neighborhood today. Nobody currently has a confirmed explanation for how it got that way so quickly. It might be the result of unexpectedly early, unexpectedly violent galactic mergers. It might be connected to an aggressive, still poorly understood, supermassive black hole. Or it might be pointing towards some genuine, still undiscovered gap in how astronomers currently model the pace of galaxy formation in the earliest chapters of cosmic history. What makes this genuinely exciting, rather than simply confusing, is that this is exactly how real scientific progress happens. A telescope reveals something nobody predicted. Researchers publish it honestly, openly, in a peer-reviewed journal, with every measurement and methodology laid out for other scientists to scrutinize and challenge, and the entire scientific community gets to spend the next several years testing competing explanations against real, hard data, slowly working toward whichever answer actually fits. That's a fundamentally different process than a single dramatic reveal, settling the question once and for all. It's slower, messier, and far more honest. And it's exactly the kind of process that has quietly built almost everything we currently understand about the universe. If you want to know the moment researchers finally figure out how a galaxy this young managed to grow old this fast, subscribe and turn on notifications, because this is exactly the kind of open question James Webb keeps turning up. And we'll be covering the answer the moment real published research actually finds it. And drop a comment telling me which explanation you find most compelling: early violent mergers, an aggressive black hole, or a genuine gap in our models of the early universe. Because honestly, after everything James Webb has already shown us about how strange the early cosmos actually was, I wouldn't rule any of them out completely.